All right, so today we're going to go through the notes on 3.5 where we're going to talk about sequences as linear functions, okay? These are kind of fun. We can relate a pattern of the pattern of team times. We're talking about team times up here from a rowing team to a linear function. A sequence is a set of numbers. It's called the terms of a sequence in a specific order. Okay, a sequence is a set of numbers called the terms of a sequence in a specific order. Look for a pattern in the information given for the women's crew team. Make a table and analyze the data. All right, so that's what we're going to try to do here. So we notice as the distance increases in regular intervals, the time increases by 1 minute and 32 seconds. Since the difference between successive terms is constant, this is called an arithmetic sequence, okay? Constant. So we're looking at like the slope is constant, okay? So it's a line. The difference between the terms is called the common difference, or D, okay? So an arithmetic sequence is a numerical pattern that increases or decreases at a constant rate called the common difference, okay? The rate here is called the common difference. And it could be up or it could be down. You'll notice right here this is 2 and this is -4. So these are the common difference. The 3 dots used within the sequence, that's called an ellipse, all right? The plural being ellipsis. The ellipsis indicates that there are more terms in the sequence that are not listed. So it implies that it keeps going, just like it does in English when we write and we're like, yeah, you know, we went here and we went there and we went all sorts of other places, ... There's more stuff that's not listed, okay? So let's look at how we use this. So real simple stuff to start. Determine whether each sequence is an arithmetic sequence and explain. So here we have -4, -2, 0, 2, and we notice that each time it's increasing by 2. So yes, that's arithmetic. This one, 1/2 to 5/8 to 3/4 to 13/16. That's kind of tough. It's easier if we look at it with a common denominator. So let's write this out as 8/16, 10/16. This would be 12/16. And then 13/16. So each time it's increasing by 2/16 or 1/8 until the last one. So this one is a no. So let's take a look at 1a. This is +4, +4, +4. So this one's a yes. This one is +3, +5, +16. So that is a no. Okay, real simple there. Real simple. Just identifying whether or not it's a sequence. Okay. Find the next 3 terms of a sequence. So you guys have been doing these patterns for a really long time. Nothing different here. So here, you know, each time it's subtracting 6. So the next 3 terms are -9, -15, -21. No big deal. Here, in the practice one, we're adding 1.5 each time. Okay, so 1.5 plus this, that's 15.5, and then 17, and then 18.5. Again, really easy stuff. You guys are probably like, oh my God, I can't believe we're doing this. Right? So, since that's how you're feeling, we'll get a little bit harder. Each term in a sequence can be expressed in terms of the first term, which is like a, and then that's not an exponent, that's like sub 1. So a sub 1 is like the first term. The second term, a sub 2, is just a sub 1 plus d, the difference. All right? And the third term, a sub 3 plus 2 times d, and then 3 times d, and then so on. So the nth term is a sub n, and that's a to the first plus whatever term it is minus 1 times d. Yeah. The nth term of an arithmetic sequence with the first term of a sub 1 and a common difference d is given by a to a sub n equals a sub 1 plus the quantity n minus 1 times d, where n is a positive integer. Whew. So, but if we look at the example here, we have 8, and then we have 8. If the terms were 8, 11, 14, 17. So we get to 11 by adding 3 to it. We get to 14 by adding 2 times 3. We get to 17 by adding 3 times 3. So that's all it's doing. Okay, so the fourth term is 3 times the difference. We do that so that what if I want to know what's the 117th term? Well, I don't want to have to add 3 each time. I just want to use this formula here. So that's why we're doing this. So write an equation for the nth term of the arithmetic sequence, -12, -8, -4, 0. So the common difference is d. So we have a sub n equals the first term, -12, plus n minus 1 times 4, which is the d. Then we can distribute the 4, and we end up with that. 4n minus 16 will give you anything you want to know, assuming that we're starting with this a sub n, the first term being negative 12. For the ninth term in the sequence, we would simply plug the 9 in for the n, and we can find out, well, what's the ninth term? If we wanted to graph these first 5 terms in sequence, okay, the first term was negative 12, the second term was negative 8, so they form a line. We can see that. Which term of the sequence is 32? So here this is a little bit backwards. We put 32 in for the a sub n, and then we solve for n, so we can find out which term it was. So let's do some practice, and we're going to do this one together, okay? Consider the sequence 3, negative 10, negative 23, negative 36. First, let's write the equation. All right, so let's do this. Let's say, all right, the general form of the equation is this up here. So let's do this. I'll do it fancy. You'll write it, and I'll do it fancy style. Okay, so we're writing this out, and we're going to use this to put in, you know, our information. So clipboard and paste. All right. Where did it go? There it is. All right, so we're going to use this as like a model. So here's our model. Well, the a sub n is what we don't know. So a at any term equals the first term, 3, plus n minus 1 times d. Well, what's the difference each time? What's the difference? It looks like we're subtracting 13, so this is negative 13. All right, and then we want to simplify this. So this is 3 plus negative 13n plus 13. So this is negative 13n plus 16. Now let's check that and see if it works. For the first term, it's 3. So 1 times negative 13 is negative 13. Negative 13 plus 16 is 3. What about the second term? Negative 13 times n is negative 26. Negative 26 plus 16 is negative 10. Looks like we got it. All right, so that's part A. 3b. Actually, let's do this. We'll change colors. That way you guys can ask questions easier. I don't understand blue. All right, 3b. Find the 15th term of the sequence. Well, the 15th term means just plug 15 in for n. So negative 13 times 15 plus 16. All right, so negative 13, and I'll use a calculator so I can seem like a regular guy. Negative 13 times 15 is that, plus 16, boom, negative 179. Okay. Graph the first 5 terms of the sequence. Here we would just sketch this, guys. You're going to have to, well, we jumped up over there. And your sketch might be different than mine. You might choose different points. I know that it's getting very negative. Okay, I know that. So let's give me some lines here. So the first term would be 1, 3. So over 1 and up 3. We'll just call that 1, 3. The second term was all the way down at negative 10. So this is 1. The second term down here, we'll just say that's negative 10. So there's that. The third term, negative 23. We'll say that's down here. And again, your graph might be different than mine. How you label these units out, really no big deal. Just as long as we know that this is 3, this is negative 10, this is negative 23. Okay, so then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Boom, this is negative 36. Okay. And so there's that one. And then one more. 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, and then 1 over, and here's that one. Okay, so we've graphed it. Which term of the sequence is negative 114? Which term of the sequence is negative 114? So here, we're going to go back to our formula, and we know the a sub n, we don't know n. So we know negative 114 equals negative 13n, this is 3d, plus 16, subtract 16 from both sides, negative 130 equals negative 13n, n must equal 10. All right, no problem. No problemo. Sequences and functions now. Sequences and functions. Okay, so let's take a look. As you can see from the example 3, the graph of the first 5 terms of the sequences lie on a line. The arithmetic sequence is in a linear function in which n is the independent variable, is the dependent variable, blah, 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 d is the slope. Okay. The formula can be written as the function f of n. So instead of, what we can do is we can use this to write out the function. Okay. Where this is the slope and that's the y-intercept. All right. While the domain of most linear functions are all real numbers, in example 3, the domain of the function is the set of counting numbers, and the range of the function is the set of integers on the line. Integers only for that one. All right, so let's take a look here. Marisol is mailing invitations to her quinceañera. The arithmetic sequence is 0.42, 0.84, 1.26, 1.68 because of postage. All right, so we want to write a function to represent this sequence. So we end up with well, obviously no invitations would be $0. So we end up just with f of n equals 0.42 n. We want to graph this. The domain of the function is the number of invitations Marisol mails, so the domain is 0, 1, 2, 3, and then so on, the ellipsis. So track the chart. The chart below shows the length of Martin's long jumps. Write a function to represent the arithmetic sequence, and then graph the function. So based on this, and again, we'll use, let's see, this time, let's use this guy. We're going to put everything in to right here. There it is. Okay. And then just like the one above it, we don't know a sub n. A sub 1 is just the first term. So the first term is 8. Plus n minus 1 times d. Okay? N minus 1 times d. So what is n minus 1? And what is the difference each time? Okay? So n minus 1, if we look up above, n minus 1 here is, we just keep that. 0.42 is the difference. And so we do the same thing down here. Okay? We're just going to plug in n minus 1, and the difference is 1.5. Alright? So then this is a sub n, and actually, we're going to make this f of n, or g of n, or q of n, it doesn't really matter. So then, let's distribute. F of n equals 8 plus 1.5 n minus 1.5. And then let's write this out like we would a line. This is 1.5 n plus 6.5. Okay? And then if we were to graph this, if we wanted to put this on a graph, let's go in here real quick. Let's grab you. Okay, so say we want to graph this. We would graph it the same way we would graph a line. His first jump was 8. Let's say each one of these is worth 2. So first, these are worth 2. So 2, 4, 6, 8, 10, 12, 14, 16. So his first jump, and these are, we'll count by ones. His first jump was worth, went 8. So to right there. His second jump, 9.5, so we'll say that's right here. His third jump went to 11 here. Fourth jump went to 12.5 here. And then we would just keep graphing until we get our points. But that's what this function looks like. We connect them here. That's fine because you know, if you want to graph the line and connect the dots, that's fine. But really, that's the graph of his jumps, and then we'll put specifically the graph of the function would look like this. And it keeps going. It doesn't keep going infinitely because obviously he can't jump you know, if he jump on his 19th jump, he's not going to jump, he's never going to jump like 1,000,000 feet or anything. So there would be some limits here, but some practical limits. But that's the graph of his. Okay? What I'd like for you guys to do is take a look, please, at 1 through 7. See if you can do those, and then we'll talk about those tomorrow in class. See you tomorrow. Bye.